Today, we are going to talk about a single theorem that completely flipped our understanding of reality on its head. It solved one of the biggest, most nagging paradoxes in all of physics, and it was done by someone you've probably never even heard of.
So let's start with a really simple question. Imagine you're out in the total emptiness of deep space, far away from any stars or planets. You take a rock and you throw it. What happens to it? I mean, according to everything we learned in school, Newton's first law says it should just keep going forever, right?
Well, here's the crazy part. In our actual, real universe, that rock would eventually slow down, and then it would stop. So what gives? Where did all of that momentum, all that energy, just go? The answer to that question baffled the greatest scientists of the 20th century, and it led to a discovery that underpins pretty much all of modern physics. Yeah, this isn't just some little trivia question. This whole rock paradox is tied directly to a massive, gaping hole in Albert Einstein's theory of general relativity, a problem that he himself couldn't solve. Okay, so picture this. It's 1915. Einstein has just come up with this beautiful, revolutionary theory of gravity. But there's a huge problem. He can't make the math show that energy is conserved. You know, that basic rule that says energy can't be created or destroyed? A brilliant mathematician, David Hilbert, he took a shot at it, and he found a solution. But here's the catch. It only worked for a universe with absolutely nothing in it, which is not our universe. Both of these genuses were completely stuck. But luckily for physics and for all of us, Hilbert knew just the person to call for help. His new assistant, an unpaid and mostly unknown mathematician named Emmy Noether. Emmy Noether's story is just wow. She wanted to be a mathematician, just like her dad, but the universities literally wouldn't let her enroll as a student. Why? Because she was a woman. But she didn't give up. She pushed through, earned her PhD, and became one of the world's top experts on this incredibly powerful idea, symmetry. And look, this wasn't some subtle, unspoken thing. The academic senate at one university put it in writing, saying that letting women in would overthrow all academic order. It's in that environment, against that kind of hostility, that Noether did her most brilliant work. So what is this big idea of symmetry that she was so good at? Well, it turns out to be something like a secret code that the entire universe is built on. The idea of symmetry is actually really simple. It's just any change you can make to something that leaves it looking exactly the same as it did before. So think of an equilateral triangle. You can spin it by 120 degrees and it looks identical. You can flip it over one of its corners and it still looks identical. Those actions, the rotations, the flips, those are its symmetries. And this is where Emmy Noether had her absolutely revolutionary insight. Her theorem proved, with mathematical certainty, that for every continuous symmetry you find in nature, there is a corresponding law of conservation. It's an unbreakable link. So, because the laws of physics are the same here as they are on the other side of the galaxy, momentum is conserved. Because the laws are the same no matter which direction you're facing, angular momentum is conserved. And this is the big one. If the laws of physics don't change over time, then energy has to be conserved. This incredible theorem gave Noether the perfect tool to finally crack Einstein's energy problem. And the answer she found came with a twist that is still, to this day, completely mind-bending. Noether took one look at the math Einstein was trying to use, and she spotted the fatal flaw right away. He was using something that was basically a mathematical cheat, a pseudo-tensor, which meant the energy you measured would literally change depending on how you were moving. That violated the absolute core principle of his own theory, that the laws of physics have to be the same for everyone, no matter what. So think about it. In a perfect, boring, static universe, the laws would be the same forever. It would have perfect time symmetry. But that's not our universe. Our universe is expanding. It was totally different in the past, hotter, denser, and it's going to be different in the future. That means it doesn't have perfect global time symmetry. So, if you follow Noether's own theorem, what does that imply about energy? It means that on the grand cosmic scale of the whole universe, energy is not conserved. That fundamental law of physics, the one we all learned in school, it's not actually fundamentally true for the universe as a whole. It's a shocking idea, right? As one physicist put it, when people ask where the disappearing energy went, the only answer is, it doesn't go anywhere. Energy's not conserved. It's just gone. And this is the answer to our puzzles from the beginning.
That photon traveling since the Big Bang, it gets stretched out by the expansion of the universe, and it loses almost all its energy. It just vanishes. And our rock thrown in deep space, it slows down because the very fabric of space-time that it's traveling through is expanding underneath it. The energy just dissipates into the cosmos.
Now, you're probably thinking, wait a second, every experiment ever done on Earth shows energy is conserved. And you're right. That's because on our human scales, seconds, days, even centuries, the universe's expansion is so tiny it's basically unnoticeable. So locally, symmetry holds and energy seems perfectly conserved. It's only over cosmic timescales that the law truly breaks down.
So with this one powerful, elegant idea, Emmy Noether didn't just fix a problem for Einstein, she laid a completely new foundation for all of physics. What she proved was that Hilbert's solution, the one that seemed useless because it didn't conserve energy globally, was actually the correct and complete answer. In a universe like ours, with its curving, expanding spacetime, you simply can't have perfect global energy conservation. The best you can ever get is local conservation. Energy is conserved in little patches, but it can leak out across the whole system.
And the impact of this, it's just impossible to overstate. Physicists started looking for symmetries everywhere. Her theorem became the mathematical bedrock of all of particle physics. It pointed the way to discovering quarks, the Higgs boson. It explained why electric charge is conserved. Her ideas literally tell us why the fundamental forces of nature exist at all. It's that big. Tragically, despite her genius, Noether's life was always a struggle. In 1933, the Nazis came to power, and she was fired from her job for being Jewish. But did she stop? No. She held classes for her students in her own home. There's even a story that a young Nazi stormtrooper would come to her, secretly, for help with his math homework. She eventually escaped to the United States, but sadly passed away not long after.
And the man whose biggest puzzle she solved, Albert Einstein, wrote her obituary. He called her the most significant creative mathematical genius thus far produced since the higher education of women began. Coming from Einstein, that says just about everything.
And all this leaves us with one last profound thought. Noether showed us that things we thought were bedrock laws of the universe, like the conservation of energy, aren't rules at all. They're just consequences of the universe's hidden symmetries. So it makes you wonder, what other deep truths about our reality are just sitting there, hiding in plain sight, waiting for us to see the pattern?